talk today is about ZUFS, which is basically a new kernel to user bridge for file system development. It's something that we're targeting for Linux, for the Linux kernel and Linux in general distribution. So originally I'm a hardware guy, so I'll start at that layer. I don't think there's anything new here, but just to get a scope, right? We're talking about several storage. Actually, I didn't have room for tape, but we have multiple generations of storage media. Just to name the main three: hard drives, flash, and persistent memory. And obviously, all of them have their own benefits. Otherwise, we wouldn't have all three of them at the same time, right? One would kill the other. But just to kind of focus the discussion today, right? If flash, like a decade ago, the flash revolution started. The main thing that flash brought to the table was sure the slight improvement in latency, but the main thing is actually random IOPS, right? I mean, the throughputs are let's say within an order of magnitude, are around the same. But mainly the IOPS, and things needed to improve for a long time in order for the application to actually realize most of the benefit, or at least, if not all, but most of the benefit that the hardware can provide, right? And this was a gradual ramp up. With persistent memory, I kind of think it's going to be similar, right? We're talking about almost a decade later. It's probably going to take several years for all the applications to actually realize, or at least for a wide range of applications to actually realize the benefit. But the benefit is not so much the IOPS. I mean, it kind of resembles the trend that the CPU industry went through, where everyone was talking for a decade about frequency. At some point, the frequency didn't really matter that much, or had other issues associated with it. And then everyone started talking about the number of cores, right? So at some point, you have enough IOPS in the system, or nearly enough, and the focus starts shifting to other things. And the thing that persistent memory brings to the table is basically latency, right? So it's all about the latency. I think you kind of heard that theme here and there throughout the day. But keep in mind, persistent memory is basically, again, memory speed and storage persistency. The cost per gigabyte is far worse than flash, which is not that far, but worse than hard drives still. And what I want you to take from this slide is the latency. That's the only word that matters here, okay? So that's basically the hardware. Now there are two types, and there's some confusion in the industry regarding several terms. NVDIMMs, non-volatile DIMMs, persistent memory, PM, and SCM, storage class memory. So I'll try to give my own interpretation, which I hope would be okay. So the first one is storage class memory, SCM. Right? This term has been for a while. It actually talks about the bit level, the technology that's being used in manufacturing to provide a single bit. Right? That's basically it. So DRAM, SRAM, 3D crosspoint, NAND flash. Okay, these are all different technologies. For storage class memory specifically, we're talking about byte addressable media, okay, at near memory speed, or at memory speed, or better than memory speed, but around that order of magnitude, right? They're all different in their capabilities. The only significant technology in the marketplace today, or in 2018, as it was conveyed earlier, is basically 3D crosspoint, right? But there are several resistive RAM and magnetic RAM competing technologies from other companies that are being sampled. They're not as close to production yet. I mean, you hear a lot of those from the last couple of years. Okay, so that's the bit level, or the byte level, or the bit level technology, right, for the media itself. Now let's talk about form factors. So persistent memory is actually about the form factor, right? How do we take this on a device level, right? So it's exactly the same definition, a byte addressable device at near memory speed. And one additional important thing is that it resides on the memory bus of the CPU, okay? So everything so the CPU basically has two different buses that it uses, right? The first one is the memory interconnect, or the memory bus. which is basically designed for low latency and has all the entire hardware cache hierarchy behind it. So the L1, the L2, the last level cache, all that. So that's basically, well, until recently was only used for DRAM. So everything is volatile there. You need to know what you're doing. But persistent memory is basically used on those slots as well, right? And it has the same kind of latencies, the same kind of low latencies and hardware caching towards the CPUs. Another option is actually the second interconnect is basically the peripheral interconnect, which is the PCI or PCI Express these days, which is actually not really designed for latency. I mean, it has low latency compared to compared to Ethernet, compared to SAS, SATA, things of that nature, just because they typically are just another step over the PCI. But the PCI is basically optimized for throughput. Okay, it means it has queues. It wants to maintain and be busy most of the time. Now that's very well if you're doing large chunks of data. If you're doing even if you're doing 4 kilobytes of data, that may be fine. But if you're actually tweaking specific bytes, 4 bytes, 8 bytes, things of that granularity, then the PCIe is really delaying you on that journey. Okay. But again, SCM technology can be used in different form factors here. It could be used as Optane, as was shown earlier, as an NVMe device over the PCIe. And it could be used as an Apache bus over the memory interconnect. Okay, so just to show you one example. Okay, this is an Apache bus NVDIMM. NVDIMM, again, is the same form factor, the DIMM form factor, just in a non-volatile wrap. So this would be both persistent memory, and part of the implementation here, well, most of the implementation here is actually storage class memory. Okay. On the other hand, if I take another persistent memory device, this one specifically is from Smart Modular. It could be Micron, could be other vendors as well. Okay. This one is actually implemented. So this is a persistent memory device or an NVDIMM-N device that's basically implemented using DRAM, flash, a controller, and some supercaps. Okay, so not every persistent memory device has to be storage class memory based. Not every storage class memory based technology needs to be used in a persistent memory form factor. Okay, there's another form factor for persistent memory. It's just a 2U box, and it's too heavy, so I don't really carry it with me for talks. Okay, so let's take this up the stack a bit. So we want to use this new hardware, right? And we want to deliver that, the benefits of that to the application, right? So if you look at this, we have the application layer, we have the hardware layer, and then we have all these software infrastructure layers in the middle. And there's a trade-off, an inherent trade-off, which was also mentioned on the last talk, between the performance we can extract and the value we can extract from that hardware, from the new hardware, and then on the other side, on the software we use, that we can leverage our legacy software and legacy infrastructure software as well. Okay, so those are kind of the metrics. If you think about it, it's not very different from NVMe. So NVMe or Flash would be the underlying technology, and okay, I'm taking you several years back. Okay, Flash would be the underlying technology. The application kind of stays the same usually, and then you have legacy form factors like the 2.5-inch SATA, for example, and you gradually mature over time to newer standards, newer software infrastructure, and so in some cases, actually, the applications also change. In most cases, they don't, but in some cases, they actually change to be more tightly integrated to the hardware, right? That has some benefits, that has some weaknesses as well as the underlying technology changes. Okay, so the first I'm going to mention 3 software approaches to use persistent memory, right? So the first one is kind of trivial. You take your legacy application, you take your legacy operating system page cache, block-based file system, BIO, everything underneath. I didn't put everything because it's kind of a long and vertical stack. But then at the end of this, you basically put a block wrapper. Right? That could be software, that could be hardware. What that does basically is it takes the byte addressable device that we had earlier, right, the persistent memory, and presents it as a block device, as a legacy block device. That's very convenient because you can reuse all the other components you have there. The disadvantage is if you only wanted to update, a counter, for example, increment a counter or something, that you now need to read, modify, write a 4K block, for example, instead of just changing those bytes or that cache line. Okay, the second approach would basically be to replace this entire infrastructure with a PM-based, persistent memory-based file system that has the advantage that the key component here, the user's application, doesn't change. It uses the same POSIX API that it has before. The main thing that, well, you can basically see that everything else did change. Everything that's the infrastructure layer did change. And that provides most of the performance that can be extracted from the device. Okay. The third approach, which is pretty vocal, is actually to take the complete, forget about all the reuse, take the application, rewrite the application, maybe use new programming models like SNIA proposed, maybe use language extensions like specific C extensions, for example, for persistent memory. But basically rewrite some portions of your application so that it can basically assume the entire role that was the software infrastructure role before, basically bring it into the application space. And then you only need a DAX-enabled file system. Sorry. You only need a DAX-enabled file system, and the DAX stands for direct access. So that provides you, basically the file system manages the device, and if you need, 1 gigabyte of persistent memory, it allocates the exact where that portion is going to be. It handles the metadata, but the actual writes to the 1 gigabyte in that example is going to be directly from the application, right? So the application is responsible for the error handling, for the writing, for evicting all the hardware caches, for everything that goes on when you're managing that. Well, not managing the device itself, but at least writing to the device and reading from it, etc. It does bypass the page cache, okay? And as you can see, there's a minimal, it's actually the minimal software infrastructure that's out there, right? So a bit about what we're doing at NetApp, and I'll start with Plexistor. So basically, we took this PM-based file system and the DAX-enabled file system, and we basically implemented one, which does both. So we call it Memory 1FS. That's M1FS. It's an internal name. And that was basically, well, that handles the data path. There's a lot of other software as well for management and things like that. But that's basically the Plexistor IP. Plexistor was founded in 2013. So it's 4 and a change years ago. Still, there are not a lot of companies that develop software for persistent memory. That's still not, I mean, the industry is taking a long time to mature the hardware, mature the ecosystem, and mature the software stack as well. And that's kind of part of why we're doing this. We want to encourage the adoption rate of persistent memory and encourage some innovation in the wide, basically, around it. Last year, Plexistor was acquired by NetApp. And as part of that, we basically decided to contribute some of the IP. Obviously, not all of it, but some of the IP, make that open source and encourage the ecosystem. As far as our solution specifically, it's designed around these aspects. So the first one I already mentioned. So the idea is to support both legacy applications that do not change and new applications that are willing to rewrite themselves and serve both of those categories. It's intended to be feature-rich, so snapshots, backups, all DR. I mean, everything that basically storage, almost everything that storage does these days, we want to bring those. It's not all about speed. It's about having all the data services, the advanced data services around that. And the last thing, there's a tight integration with NetApp product portfolio. So it's, if I go back to the original slide, right, the first one, those technologies are not there. They're there for a reason, right? The dollar per gigabyte aspects of it. So you need some multi-tiering and some auto-tiering to basically take advantage for the right data. You choose the right media or the right solution around that media at the right time. So that's our focus. And from now, I'm going to go back to ZUFS, okay, to the open source component of it. So when you're starting implementing a file system, right, one of the key first choices you need to make is if you're going to implement it in kernel or in user space. Right? Now, each one of them has their own advantages. If you're talking about kernel like XFS and ext4, those are basically, that's basically, well, should be the fastest solution, depending on the implementation, obviously. The reason for that is the system call basically brings you into kernel space. You're already there. You don't need to go back to user space if your implementation is in kernel, which is why you have the best latencies and the best performance. Well, potentially you have the best latencies and the best performance, right? User space brings its own advantages, though. The first one is portability. It's easier to move them from one operating system to another and from one distro to another. It's resilient in terms that if there is some problem, if you get some uncorrectable error, some bug in the file system, etc., you basically don't crash the entire system. You just crash that process, and you can restart it. It's simpler to add functionality and debug. I think that's kind of the main reason, and that was the reason behind Fuse, for example, to begin with. Fuse, the file system in user space, the existing bridge from kernel to user space. And if we could, we would just have used Fuse. I mean, it's just not good enough for what we need, and I'll go into details on why. But if you look at how many file system implementations on user space on top of Fuse, for example, are out there, you'll see a tremendous number. Now, given not all of them are, or maybe most of them, are not industry-grade products, right? But a lot of research in the academia and in the industry as well are basically based on Fuse, right? And we want to do something similar with these kernel to user space bridges, just something that suits persistent memory and the speeds, near memory speeds and byte addressability that we're talking about with the new media. And the final one is fewer licensing restrictions. So as you know, Linux is a GPL. That puts some burden on licenses, etc. Moving to user space is a lot easier. And again, the gap is that we're missing. We were set up to do this. We're basically missing the key component here, which is an efficient and near memory speed kernel to user bridge, right? That part was missing. So the first thing we wanted to do is basically take, look into Fuse and see if we can extend that, right? And the problem is that, like many other things, I mean, like the difference between TCP and RDMA, a lot of the core architecture of the solution has to fit the latencies and the design goals that you're talking about, right? So even that Fuse basically as a black box seems suitable, right? Because it does the same functionality, it doesn't mean that it's actually the good the best solution for the specific problem we were talking about. Just like TCP is not, I'm going to get into trouble for this, but is perhaps not the best solution for NVMe over Fabric or something like that, right? It really depends on the latencies you're trying to get to. So let's see touch on some of the differences. So you see here Fuse and you see here ZUFS or ZUFS and several different criterias. So I think the first and probably the most important thing to realize about Fuse was designed for hard drives when it was initially designed. It was then extended and optimized for flash. Okay, but there's so much you can do extending that architecture. And the reason that it works well is that the underlying assumption is that the storage is going to be very slow anyway, compared to the CPU speeds. SSDs and hard drives are kind of like the same. I mean, both of them are really, really slow. So you have to rely on software caching in DRAM, in the main memory, or in the OS page cache. And because of that, that allows you to do several things. And because of the target latencies of hundreds of microseconds, you can do queuing. And you basically, first of all, performance wasn't the first design choice or the first design restriction or requirement for Fuse. I mean, it was more about allowing things that could not have been implemented with that ease before that. And secondly, the underlying assumption is that I/O is going to be asynchronous. It's going to hit the page cache anyway, and it's going to be asynchronous. The semantics that are at hand are I/O only, so read, write, system calls, things of that nature. And the cost of the redundant copy, etc., is basically insignificant. Okay, so if you take another microsecond to copy 4 kilobytes of data, no one cares, because it's going to be hundreds of microseconds anyway, right? With persistent memory, those are very different. First of all, we bypass the page cache because there's no real benefit in software caching one near memory solution. Basically bring another one memory latency in front of another near memory latency. That kind of doesn't make sense. And the additional microsecond you spend on copying the data one more time, well, first of all, there's a bill of material around that. And secondly, that really goes into compared to the PM latencies themselves, one microsecond is more than it takes to access the device itself, right? Or about the same, depending on the media. So because of those reasons, and we wanted to extend the semantics to memory mapped semantics as well, or DAC semantics, not just I/O, and we wanted to reach those latencies, we basically built something completely different. I mean, the same functionality, the implementation itself is completely different. And so there are several aspects to it. The first aspect is that we maintain locality. Because of those speeds, we do everything in a synchronous nature. We do everything in a direct I/O sort of nature. Okay, so we write the data directly to the device, and we maintain the data on the same L1 cache, on the same CPU core that it was basically the application runs on. Okay, so the ZUFS itself is basically two parts. One is ZUF, which is in the kernel itself. The other one is Zeus, which is in user space. And then the file system SO itself. So that's kind of the basic layout. Now, we basically take the same hardware core, the same hardware thread actually, that the application runs on, and we use that both for ZUF without any context switch. Without any context switch. Then we use Zeus and the file system itself, again, without any context. We reuse, the more accurate way to say that we reuse the same hardware thread, and we keep all the data very, very local, and we don't go to any rescheduling queues or any back to the interconnect that connects all the cores, right? So we do have to context switch once in order to get back to user space, but it's structured in such a way that the penalty is actually minimal for that, right? So the penalty is not many microseconds. It's around 2 to 3 microseconds penalty for that. The second key component is the zero data copy. Okay, so we actually don't copy the data from the application to the page cache or any other buffer here, and then back to the file system itself. We basically just pass memory. We play with the page table entries in the OS in such a way that basically the file system copies the data directly from user space to its own buffers or back, depending on if it's a read or a write type of request. And the administration of those accesses are done here in ZUF itself, in the kernel. But the data itself, no byte is copied to the kernel in those scenarios, right? So It's basically like a control plane. The data plane is directly on the memory itself. So some other things are not key. I mean, those are the key things into why ZUFS basically delivers those latencies. Some of the other things are just things that took us time to develop. We already have that. For example, NUMA awareness of persistent memory between the different sockets, management of persistent memory devices, of second-tier devices like flash devices, data movers between them, things of that. Things that are really the primitives for building something. We included them in ZUFS as well. Some numbers, just to show you that it delivers on the theoretical aspects that I touched on earlier. So the red line is basically fuse, and that's actually just the penalty, the additional penalty, regardless of what the file system does, right? Just to get to the file system. And basically, again, the assumption here, the assumption here is that we're using direct I/O. I mean, we're not using the page cache, right? If you're using the page cache, that's a completely different story. Our assumption is that for persistent memory, you don't need that, and don't want that as well. So I'm not sure you can see that, but Fuse has high latency, even when it's not really. I mean, the number of IOPS is not high, right? It has high latency. It's kind of hard to see that here. And ZUFS is actually better. But the second aspect is that it really saturates at some point, right? And it doesn't scale well with the number of cores that you have and the number of IOPS that you need. And you can see the blue line here that basically it's also low, but it takes it really a long time to kind of saturate, or at least for the hardware itself to be saturated, so that you can see the additional penalty here, right? So we're talking about almost 2 million IOPS on a single mid-range server, right? Not even a fancy one. On Skylake, this would be better, where I hoped to do this in time for this talk, but we didn't have time to repeat this on Skylake. So just in summary, what I presented here is ZUFS. ZUFS is a kernel to user space bridge, a new one, just like Fuse, but more tailored for persistent memory, or let's say near memory speed devices. Doesn't have to be persistent if you want to build something that's completely in a different range, like DRAM and RDMA or something around that. But when you assume that the device itself is going to take your requests and store them pretty fast, so it's worthwhile to do it, just do the job instead of postponing it to a later working thread, which is the predominant way that storage has been done in the last decades. It's open source. You have here the links, the GitHub links, both for ZUF and for Zeus, and for some toy file system that uses Zeus, so you can see that. Our hope is that this will basically bring a lot of innovation and accelerate the PM adoption rate in the industry, which will help everyone, including NetApp. And we will welcome contribution, reviews, comments, anything of that nature. Okay, thank you.